Hello guys, welcome to my YouTube channel. My name is Dr. Linton. Previously we talked about semiconductors, and today we are going to look at n-type semiconductors. When a pentavalent impurity is added to a pure semiconductor, the resulting crystal is known as n-type semiconductor. When a pentavalent impurity is added to pure semiconductor, the resulting crystal is known as n-type semiconductor. The resulting crystal is known as n-type semiconductor. There are examples of these pentavalent impurities. Examples of pentavalent impurities, we have arsenic. Arsenic is a pentavalent impurity. When we add arsenic to a pure semiconductor, the resulting crystal is known as n-type semiconductor. Such impurities which produce an n-type semiconductors are known as donor impurities. These donor impurities help in the formation of an n-type semiconductor. Let us see the formation of n-type semiconductor. We consider a germanium crystal. Let us consider a germanium crystal. When germanium, we know germanium is a group, has 4 valence electrons in its outermost energy level. When a small amount of a pentavalent impurity, like arsenic, is added to a germanium crystal, large number of free electrons become available. The reason is arsenic has 5 electrons. Now, when we consider arsenic bonding with germanium crystal, the arsenic has 5 valence electrons. Germanium has 4 valence electrons. In the formation of a bond, covalent bonds, arsenic uses the 4 electrons with the 4 electrons of germanium to form 4 single covalent bonds. But 1 electron of arsenic is free to move, meaning this electron is rotating, is just moving in the space. It has no electron to bond with to form a covalent bond. Therefore, this electron is responsible for current conduction. If we connect a circuit, we place a voltage to this semiconductor, this electron is responsible for the current conduction. If we draw the band diagram, this is the conduction band. This is the valence band. Here, there are electrons, but the 1 electron of arsenic is around in the conduction band, meaning that when an voltage is applied to this semiconductor, the current conduction is available. We can measure some current, and this is the formation of an n-type semiconductor. Therefore, let us check on the properties and the points noted on this type of semiconductors. Let us see the points we note here, points noted on the formation of n-type semiconductor. We note here that many more electrons are produced by the addition of a pentavalent impurity. Many more electrons are produced many more electrons are produced in the formation of N-type semiconductor. Also, we note that thermal energy of room temperature still generates a few holes electron pair. However, the provided by the pentavalent impurity exceeds the number of holes. It is due to this predominance of electrons that resulting crystal is known as N-type semiconductor. That is N-type semiconductor. Let us see the formation, also another type of an impurity. When we add a trivalent impurity, what is the resulting crystal? When we add a trivalent impurity to a pure semiconductor, the resulting crystal is a p-type semiconductor. Here we use a trivalent impurity. When a trivalent impurity is used in addition or in doping an extrinsic, in doping a pure semiconductor, the resulting solution is an extrinsic semiconductor of type P, meaning that it is a positive crystal. When a small amount of a trivalent impurity is added to a pure semiconductor, the resulting crystal is a p-type. Addition of this trivalent impurity provides a large number of holes in the semiconductor. Examples of trivalent impurities, examples of trivalent impurities are, we have gallium, we have gallium. We also have here boron. These are examples of trivalent impurities. Let us see the formation of a p-type semiconductor. Again, we consider a germanium crystal. Consider a germanium crystal. When a small amount of a trivalent impurity like gallium is added to a germanium crystal, there exists a large number of holes. The reason is very simple, and you can guess. Gallium has 3 valence electrons, meaning that when a small piece of gallium is introduced to germanium crystal, a hole is created. This is because the 3 valences of gallium now bond with the 3 valences of germanium to form 3 single covalent bonds. If we have gallium here with bonding with germanium, we notice that in the 4th bond, only germanium has introduced an electron. But here is a hole. There is no, in simple terms, here is an incomplete bond. The 4th bond is incomplete. Meaning that if we introduce a small atom of gallium to a germanium crystal, a hole is created. This hole, when an energy at room temperature, when an electric field is applied here, holes are the majority charge carriers. In other words, addition of trivalent impurity has produced a large number of holes. However, the few number of holes predominate the number of electrons. The resulting crystal is known as a p-type crystal. Let us see the band diagram for this. We can see that when we draw the band diagrams, This is the valence band. This is the conduction band. We see that a hole is created here. Electrons are here, but this hole is below the forbidden gap, meaning that when an energy is introduced here, this electron in the forbidden gap can easily jump to the conduction band, when an energy is introduced. And this is the formation of an p-type semiconductor. Let us see the properties of semiconductors. Properties of semiconductors. We see that the property number one of this semiconductor is that they have negative temperature coefficient. When the temperature is increased, the conductivity of these semiconductors increases. Whereas when the temperature is decreased, the bonds, covalent bonds, are stronger, meaning that the electrons are tightly held by these covalent bonds. Meaning that when the temperature increases, the conductivity of the semiconductors appreciably increases with respect to temperature. Another one is that the resistivity of the semiconductors is less than that of insulators, but greater than that of conductors. The resistivity of semiconductors is greater than that of conductors, but less than that of insulators. The resistivity of semiconductors is greater than that of conductors, but less than that of insulators. We can see the effects of temperature on semiconductors. Effects of temperature on semiconductors. At absolute zero temperature, the semiconductors do not conduct because the covalent bonds are very strong. They are tightly held. But at absolute above zero temperature, we see that at room temperature, the covalent bonds are broken. When covalent bond breaks, meaning that the electrons are free to move, and therefore the electrons are responsible for the conduction of current in semiconductors. Thank you so much, my viewers, for viewing this video. Ensure that you have shared it, liked it, and subscribed to my channel for more videos like this. Thank you.